Oh, good morning, sir.
Good morning. Good morning. So in your case,
Thank
I
you.
think it's good afternoon already, right?
Yeah, in India, sir, it is afternoon, sir.
Yeah. Okay.
Thank you, sir, for joining us and accepting
Yeah.
our invitation.
Today it is very hectic day for me. Yeah.
Yes, sir, exactly. We got the
So,
idea that you must be having multiple meetings, and in that
yeah.
timing, you are actually taking out some time. So that would be very humble of you, sir. Thank you, sir.
No, that's all good because I miss my academics now. Definitely, as I'm in industry, it's good to interact with you guys time to time. But again, this time is very hectic. Yeah. Because anyway, we have a parallel work going on with Bangalore team and also USA. So you can understand, friends, morning to night is all
Yes,
packed.
sir.
Yeah.
Yes, exactly, sir. So, sir, with your permission, can we start with the session?
Yeah. Please go ahead.
Good afternoon, participants. We're starting with our next plenary talk. The talk will be delivered by Dr. Writam Banerjee. I will be giving you a short description of our speaker. Dr. Banerjee is presently working as a principal engineer at Fab 1 Tech and Integration GlobalFoundries, Germany. Prior to this, he was associated with the Department of Material Science and Engineering at Pohang University of Science and Technology, South Korea. From 2014 to 18, he has worked as the assistant professor of Institute of Microelectronics of Chinese Academy of Science at Beijing, China. From 2012 to 13, he has held the position of visiting scientist at Zurich Research Center, Germany. Dr. Banerjee has received his PhD degree in electronics engineering from Changgung University, Taiwan in 2012. Prior to that, he has graduated from the Vidyasagar University in India. His research interests include advanced memory devices and applications. Sir, now the floor is all yours. Kindly start with your talk, sir.
Thanks, Mank. At first, I'd like to um, say thank you to all of the hosts for this conference. And nevertheless, and also I'm thankful to the audience. Well, I may not know all of you, but I think you guys are doing great in academics and also in your personal life. So let us jump into the topic. Let me share my screen first. So, can you see my screen?
Yes, sir, we can see
Is
it.
it visible? I don't know where is the pointer. Ah, okay. Great. So, like this. Okay. So today we are going to discuss about the hafnium oxide, which is a multifunctional oxide, and mostly we'll focus for the applications of hafnium oxide. And since I'm working on this, so mostly the talk will cover the how we can utilize hafnium oxide and its properties in resistive switching devices. And later on, I will show you the prospect of hafnium oxide as a material for applications and some of the applications of it. And then I will give a brief summary of the ferroelectric switching in hafnium oxide based devices, and then I will finally conclude my talk. Okay. So before we jump into the presentation, I would like to acknowledge my uh, co my co-worker in this work, especially for hafnium oxide-based devices, Dr. Kashir. He is from another company, Ferroelectric Memory, in Germany, and also Dr. Kamba. He is from the Czech Republic of Science Institute of Physics. So without their help, it was not possible to actually do this mammoth task. And for those who are really interested in hafnium oxide-based devices or in resistive switching or ferroelectric devices, for more detail, you can go through those materials. So today I'm going to cover most of them, and especially this is the review for only for hafnium oxide, the small one, which is very recently published by the group. So okay, so here's the outline of the talk. At first, I'll give you some brief introduction, and then I'll jump into the vacancy formation in hafnium oxide and what is the role of those vacancies in switching, and metal filamentary switching. I'll introduce how those metal species actually can create the properties, change the switching properties of hafnium oxide. And then we'll jump to the hybrid filamentary switching, which is basically a combination of metal and vacancies. And after that, I'll do some performance analysis with applications. And then I'll go for the hafnium oxide based ferroelectric devices. And finally, I'll summarize the talk. So, as you all know that recently we are very much focusing on neuromorphic computing stuff. And the figure in this is basically the flow of the neuromorphic computing, or maybe you can say example of this image processing, and there are many other like voice recognition, speech recognition. So there could be many several advantages of those emerging technologies. But to achieve those emerging technologies or fulfill the requirement, we have to follow the path of building the devices. And in this case, I must say that we have several emerging candidates. Normally, this is one of the major selection, that how those neuromorphic devices can behave. So the origin is from the emerging devices. So we have to very much focus in those emerging devices and their behavior. So here are several emerging devices I have plotted. So starting from the PCM, phase change memory, it is, though it is not very new, it is already in industry are really exploring these PCM devices, especially IBM, DG Watson, they have done a lot of work on that. And then it's resistive switching devices, MRAM is going on, GF is also working on MRAM, and ferroelectric devices. So those are the emerging capabilities they can have for the neuromorphic applications. So now, if we combine all of those devices and their application areas, we can actually come up with the solution, or maybe the statement like the resistive switching devices, it is equivalently useful for as a storage class memory or low power computing, with applications for electronic signups, hardware security. So this is one of the key contribution in the emerging memory devices towards the neuromorphic computing or emerging applications and all of them. And the interesting point, it will be the low power computing. Definitely power consumption is one of the key criteria to adopt any kind of new technology. So it would be that we must focus on the power, endurance, retention. So those three topics to get any kind of devices. So here is a basic diagram of the resistive switching devices. I'm not very sure that how much of you guys are working on this technology, but hope you already have the basic understanding of the resistive switching devices. In general, it is a two-terminal device, and it can have one top electrode, bottom electrode, sandwiched oxide, and the switching can happen through the oxide by forming the filament. So this is one of the example how the filament is forming with the oxygen vacancies. However, there is possibility of the formation of metal bridge, and also there is another possibility to have the switching by the interface. Okay, so there are several categories of resistive switching devices. However, mostly we are focusing here today for only for the filamentary switching devices, and for low power operation and stable performance with high device yield. So here is the basic diagram of switching diagram and how the device work. As you can see, the first the figure at the this one, it is the IV characteristics of a silver, oxide, and platinum stack. So initially you are in the very high resistance state, and After that, you are constantly increasing your bias. You are in the positive bias. So basically, you are forming the bridge. Uh, yeah. So basically, it's going there, silver ions, and then the bridge formation started. And when you have the bridge, metal bridge, so you are already in the low resistance state, and you can maintain this low resistance state until unless you apply the negative voltage. So at some voltage you can break the bridge and the device will go back to the high resistance state. So this is how the device can switch back and forth from the low resistance state to the high resistance state. And the figure here, you can see this cartoon. It is how the filament is forming and the shape of the filament. Please look very carefully into this picture. You can see a very thick filament in this case, the first case. Okay. Now, if you have a thick filament, basically you need a higher amount of voltage for this situation is true specifically for silver-based devices. And it depends on the current compliance, definitely. But you need a higher amount of voltage to break the filament. But on the other case, if you have a very thin filament, definitely you need a very lower voltage to break that. So in that sense, we can distribute this technology in a two part. The first part, it will be the memory switching, and the second part, it will be the threshold switching. This one is the threshold switching. So for the two condition, the memory switching, it must be thick filament and stable filament. Threshold switching, it must be thin filament and unstable filament. So there are many materials and systems, design systems are available. You can do a literature survey and you can find many possibilities there. But the important criteria to design this kind of devices is the selection of materials for the bottom electrode, top electrode, and also the switching layer. So now if you focus in this cartoon, and you can see we have M electrode is just a metal. It can be either way, like bottom or top of bottom, whatever it is. But the interesting point, it should be near the interface. It could be either one. Okay. So we have to choose our material very precisely, and we must understand the behavior, how behavior in the sense like when you are doing the processing, how the material can change. For example, if you have tungsten as your bottom electrode, and now you are depositing silicon dioxide or hafnium oxide by your sputtering system with oxygen environment, what will happen? It will create the tungsten oxide interface. Okay. And usually I have seen the thick interface of the tungsten oxide. So it depends what kind of material we are choosing and how we are actually preparing the stack. So that is the reason I listed here. It can be deposited by ALD, PVD, CVD, PLD, oxidation, sol gel, what else? So, but the major criteria, please keep in mind that we need to take care about the interface. So everything is going on the interface. Okay. And now defect engineering can make a big part or contribution to forming or dissolution of the filament and to enhance the performance of those devices. Now, as I told you, there are several materials available. Okay. But there's a reason to choose hafnium oxide for this talk. I try to summarize the hafnium oxide here. As you can see, hafnium oxide, it can have three different structures: cubic, tetragonal, monoclinic, or also orthorhombic structure is there, but I didn't list it here. Normally, if you can just go for the in the temperature scale, basically from cubic to monoclinic or decreasing temperature. And now for the hafnium oxide, you can have a dielectric constant. Your hafnium oxide, it should be around 25. Yeah. So the dielectric constant is around 25 and your band gap is 5.6. So now, why the dielectric constant is important, I hope you guys have the understanding of the EOT. EOT is the electric equivalent oxide thickness. So normally the current technology, which is the flash technology, it is based on the oxide, right? So now the scaling of the flash memory devices seems to be very difficult with this silicon oxide because of several issues. But I would like to highlight this dielectric constant. Now, if you have a higher dielectric constant material, okay, and a reasonable band gap, okay, and then you can actually increase the thickness of your oxide stack. So now, just for sake of understanding, if you have a 2 nanometer of silicon dioxide, then definitely with those specifications, you can have hafnium oxide like almost 12 nanometer. Okay, so that is one of the selection criteria for any new material. Okay, and then with the doping uh, in hafnium oxide, it is possible to reach high dielectric constant with a large band gap. You can see here it is like almost 65 dielectric constant with almost 6 electron volt band gap. So those kind of modifications are possible with hafnium oxide. So that is the reason it is very much useful material, not only for resistive switching devices, however, it is suitable for any emerging memory devices. Okay. But remember, I'm not talking about the phase change memory, because hafnium oxide is not illustrated in phase change memory in detail. So it is based on some other different material where they can change the phase of the material from crystalline to amorphous. Well, so the key element for resistive switching memory is the oxygen vacancies. So we are going to utilize those oxygen vacancies of hafnium oxide. And then the key element for ferroelectric memory devices is the structure. Okay, so the structural change can introduce this ferroelectric phase in the hafnium oxide, which will be discussed later. So now let us jump into the vacancy formation. As you can see in this figure, this is the gate leakage with the stress time. As you can see, it is increasing constantly. But the important factor is here, figure this and the bottom one. You can see when you increase the voltage, uh, basically you increase the voltage and the stress time. So basically your noise is increasing. Okay, and this is true for both figures. So now the important message from this one is actually calculated in the density of state as plotted here. So normally if you have pure hafnium oxide, okay, then your mid gap is completely okay, completely clean. However, if you change the composition, this is the stoichiometry HfO2, but if you are just moving down to some non-stoichiometry stuff, so what you are doing here, you are actually introducing some mid gap energies. So those mid gap energies are actually vacancies. So you can easily understand, like if HfO2 is here, this one is 1.9, and it is going to continuously gradually decrease. So in this case, I would like to mention that I personally work with those kind of changes of hafnium oxide, and modification was done from HfO2 to HfO 1.8, and we have actually found that for any kind of switching devices, HfO 1.9 is a very suitable candidate. Okay, and normally this kind of devices, it can have like die vacancies, as you can see in this picture. So normally the hafnium oxide can lose actually those oxygens, and then it can form the die vacancy, and that die vacancy can form the chain, which actually help the formation of the filament and in the switching process. So here is a typical hafnium oxide based VCM devices. You can see this is the bottom electrode, platinum, and on top of the platinum, it was HF, the thin layer. It was like around 5 nanometer thick. And then it was 10 Ti on the top. Okay, so the stack in simple way, we can say that this is the top electrode, Ti, oxide layer, HfO2, and platinum. That's it. It's a very simple stack. And you can see the switching properties here from 5 microampere to 75 microampere. So it can actually gradually change the resistive switching behavior from a thin to thicker filament. So definitely you see the reset current is increasing and all of those stuff. However, the nonlinear behavior of the low resistance state, it was fixed because it is the same filament, is just thicker or thinner, and that's it. Then this is one of the major issue. Now, as you can see, we are using hafnium oxide, but hafnium is actually is a substitutional element. Like if we dope hafnium in any system, it cannot form the filament. Okay. However, there are several other elements like copper and silver. This is the mostly used materials which can easily form the filament. As you can see, the formation energy for interstitial dopant is very low for those kind of stuff, and also nickel is very much used to understand this thermoelectric driven behavior. However, please concentrate in copper and silver. So basically, copper and silver, those materials are very likely to diffuse inside the system and take a part in the formation of the filament. Okay. So those things are basically the interstitial dopant. So if you have interstitial dopant inside the system, so you can blindly say that this is a metal filament which is going to take place in your devices. However, if you have a substitutional dopant in the system, then it is most likely to have a oxygen vacancy driven filament. So in this case, we have like substitutional type of things inside the switching layer. So definitely we have an oxygen vacancy filament. Sorry. Sorry, is someone asking something?
No, sir. Actually, there is a, I think, background noise. Please continue.
Ah, okay. Okay, okay, okay. So let us move to the um, metal-based switching devices. So how the metal filamentary switching devices can actually play the role. So the stack should be the same. Here, as you can see, this is the hafnium oxide, and in this case, we have just used silver, and the contact is PT, platinum, or IR, and this analysis was done by conductive AFM. Now, just to understand those behaviors and how the metals actually are diffusing through the film, the graphene layer was used in this case, and the graphene layer was actually patterned with this Olympic ring structure to understand how the diffusion can possible through the graphene layer, the broken part of those layer, and the rest of the part, it should be the high resistance state. So as you can see, the forming initially without any forming event is going to be a dark film, but then during the forming process, this diffusion of copper actually gives you the uh, Olympic ring structure. So very clearly you can see that there's a contrast between the Olympic ring structure. So basically dark and white. So white is the high current region and dark is the low current region. So low current region is basically the high resistance state and high current region is basically the low resistance state. Okay. So now when you do the erase state, you can see it's completely gone. So it means that now in this situation, none of the silver particles stay inside the system. At least it is not detectable. Okay, so this is how the switching can happen in metal based devices. The similar kind of analysis was done using the high resistance, sorry, HRTM image, and the analysis is here. However, the analysis actually it is very difficult to find out the exact location of the filament, but from the analysis, it shows that copper is definitely present inside the filament structure. So nevertheless, the story is that if you have a system based on interstitial defect, so definitely you have a formation of the metal filament, not the vacancy filament. And now if you have a substitutional defect based system, you have a oxide filament. So this is how we can distinguish the resistive switching devices in a two-part. Now, here is a new concept we have introduced in a few years back. It was electrically controllable brake junction. So I'm not very sure that if you have heard the term controllable brake junction or mechanically controllable brake junction, MCBJ, but this is very similar concept. In MCBJ, mechanical controllable brake junction, you have to apply some mechanical stress to pull or push those junctions And in this case, we can actually use the electrical pulses to create those junctions. So basically, a single junction formation is possible, and also there is the evidence of a single atomic switching through this kind of experiment. Well, this is the first measurement. This is the forming measurement, or during the set measurement. It was done under the current pulse mode, and as you can see that the sweep of um, the sweep shows that all of those state nicely fitted with the quantum point contact model. So this is from 1 G0 level up to 22 G0 level. Okay, so in a shorter term, we can say that a thick filament is actually building up inside the device. So 1 G0 actually can refer to this small red junction, and slowly it can increase the filament, and it can increase like several atomic contact. Okay, now when we apply the negative bias on that, so this is the reset process. You can see initially we were at 22 G0, and slowly the filament was broken. Now the 10 G0 show a nice breakdown. From the 10 G0 to 1 G0, we can almost stress most of the uh, conductances. So basically you can imagine this is like if you have a 10 atoms connected together, so with a certain amount of pulse voltage, we can reduce that atom from 10 G0 level to a single G0 level. So it is just like you are removing the petals one by one. Okay, so this was a nice experiment to actually explain how this break junction can introduce a single atom switch in the CBRAM type of devices. However, on a practical note, this demonstration was nice, but on a practical uh, design, this is a very difficult one to have the uniformity over the wafer. Okay. So here is the impact of the different electrode materials. Again, I want to say one point, like as you can see here, the structure is the bottom one. This is the Ti and nitride. So basically thinitride in the bottom. Oxygen was over the stack, and hafnium was very much concentrated here. Again, Ti is on the top. So basically in this case, the structure was Ti on top, and then you have hafnium oxide, and then you have this region. It could be Ti oxynitride stuff, and then you have TIN. Now, if you check here in this diagram, you can find that the formation of the Ti oxynitride is somewhere near to this, this place. Okay, yeah, or maybe it could be a little bit lower. Okay, however, the point is, if you have Ti at the bottom surface and the deposition of hafnium oxide, in this case it was by ALD. Okay, so the probability of oxidation was very less, but if you have the sputtering system, definitely it will create the oxygen on the surface. Okay, so it could be Ti oxynitride, ON. However, that oxynitride, it can act as a source of oxygen vacancies, because that film will not be the stoichiometry, and it will have many vacancies inside. Now, instead of doing that, if you have a Ti, you will form a thick Ti oxide film, which is again create the bilayer structure. So this is how the impact of the electrode material and its location. Okay, so it can change depending on the design. And then the second part here, you can see that there are several electrode materials. So based on those electrode materials, some of them, they can actually show the yield of the memory switching is changing. So some of them, they can show the memory switching behavior, and some of them, they can show the threshold switching behavior. So the first two, like tungsten and copper, they are showing a very high yield for the memory switching behavior. However, for silver, and silver tellurium, or maybe any silver-based devices, they are showing the high yield for the threshold switching behavior. So this is how the switching can be designed. There is another possibility to design the electrode material for resistive switching devices, ultra thin, as you can see, the thin monolayer graphene sheet. Okay, and also the device design is possible with reduced graphene oxide. So there are several ways to design the resistive switching devices, but it depends the conditions and need. Okay. Well, now we'll move to the hybrid filamentary switching. So definitely, so far we have understood the oxygen-driven filament, oxygen vacancy-driven filament, which is the first case, and the second case, which is the metal filament. Okay. Now, the problem is in a switching stack, in general, we do not have a pure material like silicon dioxide or hafnium oxide or whatever it is. But the thing is that we already have the defective material, defect species inside. So now if we have a defect species already inside and you are using the metal on top, how you can avoid the impact of those defects? Okay, so there is a nice paper was presented by uh, Letty, and they have shown that the oxygen vacancies actually can take place even the switching is based on the metal filament. Okay, so the proposal in this case, it was the formation of the hybrid filamentary switching rather than is just a simple oxide RAM or CBRAM device. So the rest of the topic I'm going to cover within very quick time is like hybrid filamentary switching and how we can modify this one. So again, here is the simple hafnium oxide based device. Is a simple silver, hafnium oxide, and platinum. The structure you can understand, this green layer is the hafnium oxide and yellow one is the silver. Okay, now the initial physical analysis was started from here, the understanding of the XPS behavior, and the XPS analysis shown that in our case, if we deposit the system using the PELD system, then we can have a stoichiometry hafnium oxide. However, if we deposit by ALD with O, we can go for 1.9 stoichiometry. And if you check the density of the film, so definitely for HfO2, the film density was quite high. Okay. And for 1.9, the density was like 9.42 gram per centimeter cube. Okay. So we choose this one because we can have a lesser forming voltage and other advantages as compared to the pure hafnium oxide HfO2 structure, because we already have some amount of defect inside. So now we are going to deal with those defects along with the interstitial metal like silver. So we started from the threshold switching behavior, and to obtain this one, we have done several schemes. And usually we found that the negative, like pre-forming step, negative before positive step, it actually improved the device yield up to 90%. And here is the basic control of the filament. Initially, we started from the negative side, and then we form, so the negative side will form the oxide filament. Okay, and now when you switch to the positive side, this positive side will form the silver filament. So you already have the path of the oxide filament, and then silver diffuse through the path and basically form the hybrid filament. And with this type of concept, we achieve a nice threshold switching behavior. As you can see, the sharp transition from the high resistance state to the low resistance state with a selectivity of 10 to the power 9. Well, previously threshold switching behavior reported with high instability. So this is one of the major concern of resistive switching devices till now. Okay, even the companies are suffering the same problem. The stability is the main issue. Then already you can see in this figure that the variation was for the single direction or maybe for bidirectional, whatever it is. The major reason of this failure was the over diffusion of silver, because there was no guidance to the diffusion of the silver through the stack. Okay. So to understand those behavior, we have done the DFT calculations, and we have found that if the oxygen vacancy is present inside the system, then definitely the forming energy is the lower one for the silver filament. So basically, if we have silver plus vacancies, the forming energy is very low and the switching is very stable. Here is one example. You have 1,000 switching cycles for each level and the devices achieve with a high stability. However, the problem with the only silver based devices, it was again, we are successfully control the diffusion of silver through the channel, but still there was something limiting to achieve the longer endurance, because you can understand, if you have a source on top, silver source, and nothing is there to hold it back. So definitely, although you have a thin channel, but still there is a possibility for the other diffusion probabilities of the silver into the switching stack. However, if you go for a alloy electrode like silver tellurium, then definitely the probability of the diffusion is very less, because Te is holding the silver back. Okay. So normally you can achieve the very good threshold switching behavior if you have silver tellurium, and the failure probability of those two devices are totally different. The first one, the red one, is the silver devices. You can see the probability of conductance increase is very high, but the failure probability of the silver tellurium, it is actually the opposite direction. It is going to fail in the higher resistance side. So basically, you are with the erasing cycles, you are removing the silver from the stack. So for the threshold switching devices, a fragile electrode has a fragile design is the best selection. So basically, silver tellurium is a good selection for threshold switching behavior. So to understand this one, we have studied the nucleation model and mechanism. So as you can see in the nucleation model, so basically you have a critical radius of the nucleus, and above that region, this is the growth phase, and below that, this is the nucleation phase. So threshold switching devices are always better to operate within the nucleation phase, not the growth phase. Okay. So when we design this structure, so the silver tellurium is the best candidate to provide the nucleation phase longer. So basically, when you continuously do the program cycle, so you have no problem with the filament stability. Okay. Now, we check the endurance measurement of those devices, and we have achieved a record endurance of 10 to the power 9. Well, this endurance actually measured by Intel, because this project was also funded by Intel. So it was nice threshold switching endurance, which we have achieved using this methodology. Okay, so now what will happen if we go beyond to the threshold switching? So if we go beyond through the threshold switching and increase the current compliance, it will give a very strong filament. Okay, so basically for the threshold switching, you are operating here, and this is almost like 3 to 4 atomic contact. So this can create the junction. So basically 3 to 4 atomic contact, it can be your critical radius, but again, it depends on the stack. Okay, but mostly it is 3 to 4 atomic contact. It can be the critical radius for the junction. And once you have like fifth atom additional to that, so you are already in the memory switching zone. Okay. So here is the performance of the memory switching zone. As I told you, the preforming is important. So here also we have done the preforming for -6, like microampere level. And then the same device, silver hafnium oxide PT, rather than showing the threshold switching, you can see that it has a surf transition forming, and then you need a reset voltage to reset the device. So this is how we can switch a threshold switching device or selector device to a complete memory behavior. And here is the memory switching behavior of the same device. And apart from having a threshold switching, we have well-controlled memory behavior in both like high resistance state with increasing stop voltage, and also you can see the different levels in the low resistance state with increasing the current compliance. So minimum level was like 50 microampere, we can achieve the good switching. However, mostly 100 microampere or 200 microampere was stable range. Now, to understand and go further to understand those behavior, here is two examples. The first one is only for the metal devices, metal-based CBRAM. You can see that metal-based CBRAM devices, they can show the clear integer conductance jump from 10G0, 9G0, 8G0, something like that. But if you have a vacancy-based system, then you can have the half integer number inside the conductance jump. So basically those vacancies are creating some they have major influence in this filament. So when you test this one with a different vacancy concentration, like from 10 nanoampere to 10 microampere, well, I do not have the exact number of vacancies, but definitely, you know, from the oxide breakdown, if we have a larger current, definitely there is a generation of high amount and strong path for the leakage breakdown. So basically it will generate the high number of vacancies. So when we have the pre-forming condition like 10 nanoampere, we have a very few amount of vacancies. So along with the integer path, we have very less, like two half integer path count. But when you increase this one, the pre-forming condition, you can see we actually increase the half integer condition inside the stack. So basically now we have 3 to 4 half integer values. Again, when we go for 10 microampere, you see the reset is like the gradual reset. And we have actually increased the half integer peaks very often. Okay. So this is how we can introduce both the metal filament and the oxygen vacancies together inside the structure. Okay. Now, if you tune the structure, here is a full summary from the threshold switching to the memory switching. Basically, what you are doing, you are changing this high resistance state. So very much starting from the 100 picoampere to 10 microampere. So you can see 100 picoampere and then nanoampere, 10 nanoampere, 1 microampere, and this one like, sorry, yeah, this is 10 microampere and yeah, so as you can see, the high resistance state is actually changing from very high value to a low value. And also, additionally, this reset behavior, it was very steep and it changes to gradual reset process. So this is how we can actually tune the structure. And this is a report from Sematech. It also confirmed that with the current level, we can actually generate huge number of defects if we have a higher current level. So definitely the generation of the defect is more. Okay, so and here is the DFT calculations to understand this one. And the same story is true again. So we have in the DFT calculations, we have seen that if we have a current level like nanoampere and microampere, the nanoampere bridge can show only a small filament, but the microampere actually can introduce a large filament. So basically, if you have a large and thick filament, it is a memory switching. And if you have a thin filament, it is a threshold switching device. Okay. And in the same device, we have achieved excellent memory switching behavior, as you can see, a continuous loop. And here is the endurance and retention performance. So we have achieved this endurance up to 10 to the power 8 cycles. Well, the rest of the part was not measured. And the retention was achieved for 150 degrees centigrade. Okay. So in overall summary, we can see that we have achieved the retention, which is almost 70 degrees centigrade for silver-based devices, which is a very difficult job because silver-based devices are usually used for threshold switching devices, not memory switching devices. But if we have this kind of modulation of the filament, then we can introduce the retention for a very longer time. Okay. So the similar story was also reported, I guess, by Sony in VLSA 2019. Okay. So here is the performance summary comparison for the threshold switching devices. With this hybrid filamentary switching, we can achieve a nice threshold switching behavior with high selectivity of 10 to the power 9, high endurance of 10 to the power 9, and the performance of hafnium oxide based devices, you can see with the thinning of the oxide stack, we even can achieve the forming free device. And if we go for the power comparison, the threshold switch, the memory switching devices of hafnium oxide, it can actually achieve below 100 picosecond. And yeah, below 100 picosecond, even for the high temperatures. And then for multi-level, it is possible to achieve the 6 bit per cell. And for cycles, the maximum cycle is possible to achieve like 10 to the 10 by maintaining a memory window around working memory around 10 to the 3. And depending on the design of the stack, we can actually get different retention behavior. So the highest one, it was actually achieved for almost 200 degrees centigrade, but with a 10 G0 contact. So if you have a thicker filament, your retention will be much better, because you can see for 1 G0, even for the room temperature, it can be difficult sometimes. For the room temperature, copper-based hafnium oxide, you need at least 5 G0 filament to have a good retention behavior. So here is a comparison with the other materials. So please remember, this all data are not from the same device size, because you can see the device area was different, the stack was different. It is just the comparison, the prospect of the material. So for hafnium oxide, already the best part was that the oxide thickness was scalable so far, 2 to 3 nanometer, and the device area scalability shows like 10 nanometer square area. The speed is less than 100 picosecond, and margin is quite high with a 6 bit per cell storage, and the switching energy is very low, less than 0.1 picojoule, and retention was like 200 degrees centigrade for 10 to the power 8 second is, and endurance was 10 to the 10. Okay. However, some parameters are little lower than the other reported by other group, like 10 to the 12 for tantalum oxide reported by Samsung, and also for other bilayer structure, it is reported the scalability of the stack was like 2 cross 2 nanometer square. So that much smaller area is possible only for the interface devices, not for the filamentary devices, because itself the filament, it can consume some amount of space in your switching stack. Well, now the applications of those hafnium oxide based devices. So this is complete picture is based on the hafnium oxide. So it is definitely, it can be possible for 1T1R cell, but at the same time, already 3D integration scheme is shown for the hafnium oxide based devices. So again, it was the similar structure is like tantalum nitride, hafnium oxide, and Ti. Those devices are very much applicable for like neuromorphic computing. Here, I just have one example how the devices based on hafnium oxide, it actually can reduce the energy of the spike. So like for the hafnium oxide based devices, it is possible to achieve a very low energy per spike. Okay, so that is how those devices can be useful for the low energy applications. There's the other application possibility in the security domain. So now here, please keep in mind the the switching, it can be a stable one or unstable one. Now, when it is a very stable switching, then it is very much useful to apply in the memory type of application or maybe neuromorphic applications. However, if you have random defects and random state variation, this is also useful for security application, just like true number generator trang applications. So basically, it can give you a random state over the time. So that is how these systems can be useful for hardware security. So now let us just quick review the last topic, which is the hafnium oxide based ferroelectric devices. Here is just a summary of the ferroelectric devices. Well, this is not my core domain, so I may not be the right person to or not authorized to discuss those full detail, because my colleague Dr. Ali, he was the in charge of this one. Well, but I will summarize this one. Normally, hafnium oxide, it can have many different phases, as I told you previously. So if the phase changes from one phase to another, this can actually produce the ferroelectric behavior inside the system. So now to change the ferroelectric phase, we can dope different materials. So normally, hafnium zirconium is one of the mostly used system which can show this hysteresis loop, as you can see. But please keep in mind, there are several parameters which can actually create the problem in the stack. It is just that it very much depends on the grain, right? So then if you have a too much grain inside the stack, it can produce too much pressure inside the structure. So it is not good. So basically it is better to have a larger grain to have a lesser internal stress. And then to increase the grain size, this capping effect is just the electrode effect is very much important. So now if you have the thermal expansion coefficient of any electrode, which is lower than the hafnium oxide, that is a very good selection to improve the ferroelectric behavior in this kind of devices. But remember that vacancies are killer here. Vacancies are only useful for resistive switching, but not in ferroelectric devices. Okay. So in summary, hafnium oxide is an excellent candidate for emerging memory domain, and the scope of hafnium oxide is already explored for resistive switching devices such as VCM, ECM, filamentary, interfacial, hybrid, and other devices. And excellent resistive switching behavior for hafnium oxide based RRAM is already achieved, like sub nano second speed, 6 bit per cell, MLC, 10 to the 10 endurance cycle, 10 years of retention at high temperature. And those emerging behavior of those ferroelectric behavior actually boost this material to explore more in future for any kind of emerging memory applications. So if you are interested in this topic, please you can check the Google Scholar and or maybe is so many articles are available. So please check it and you can have more information. Thank you.
Thank you, Dr. Banerjee, for such a wonderful talk. Now the participants on the floor is open for any questions. If somebody has any question, they can kindly unmute themselves.
Good afternoon, sir. Thank you for a very nice presentation. I have a question regarding fifth or sixth slide where you have discussed about silver-based devices having high or thick filament.
Which slide? Sorry.
So AG-based devices having which is showing thick and thin filament formation.
Okay. Actually, the whole topic is based on that. So, so can you? So is it
earlier, sir? Earlier.
Sorry, earlier.
It is earlier.
Okay. Okay. So can you see my
Yes, sir. Yes, sir.
the left hand side?
Yes,
So
sir.
please let me know which.
Yes, sir.
So maybe earlier.
Yes, sir.
Okay.
Between 5 to 15, I think.
Sorry.
5 to 15.
Okay. 5. Okay. So it was like in. Okay. So 15 is here. Is it this one or the introduction? So basically
Sir,
5.
this one. Eighth.
This 8. Okay. Yeah.
Sir, while explaining this,
Hello.
hello.
Sir, kindly share your slide again. I think some participant has actually taken over the control, so might be your control has been lost. So if possible,
Okay.
kindly share your screen
Yeah.
once again.
Sure. Yeah. We are here.
Like while explaining memory switching, you told that silver-based devices show thick filament formation. So, is there any property or specific reason why this silver shows thick filament formation, not thin?
Yeah, silver also show thin filament formation. The first criteria is that what is your current level. So now if you have, I'm talking about single device, 1R, okay. So if you have a thick filament and it is only possible if you have a high current level. So let me go back to this picture. Just yeah, here. So this is also silver-based device. Okay. So the thick filament is only possible when you operate the device more than 100 microampere with this scheme. So normally it could be like 1 milliampere. So if you have higher the compliance, then it will definitely a thick filament. But if you have a lower compliance, then definitely the diffusion of silver is much less. So now if you have a very less amount of silver inside your switching stack, it will form a very thin filament. So in this case, if you're going to measure a two-terminal device, then please keep in mind that your current limit is playing a key role that how your switching will behave.
Okay, sir. Sir, I have one more question. Is it
Yeah, sure.
possible? Is it possible to means control whether we can do filamentary switching or interfacial switching?
Well, it depends. As I told you, it depends on your switching stack. Okay.
Okay, sir.
So if you have hafnium oxide based devices, then no, you will have only filamentary switching. But again, if you have like aluminum oxide as your tunnel barrier, then it will be a filamentary, but at the thin tunnel junction, you can have some amount of changes, different changes. So it actually very much depends on the material selection and the combination of the material. So there is a work from IMEC, which is based on hafnium oxide and aluminum oxide, and they have done 1 nanometer of aluminum oxide to control it within that range. But it was not interface, it was filamentary. But for interface switching devices, I think you can design Schottky junctions and you can have interface kind of behavior. Yeah.
Okay, thank you, sir.
Any other questions from anyone?
Any other questions from the participant side? So I think there is no further question from the participant side. So let's thank our speaker. Thank you, Dr. Banerjee, for such an informative talk. And
Thanks a lot. Thanks a lot.
we definitely, we humbly thank you. You have accepted our invitation to deliver such an interesting talk at our platform. So thank you.
Yeah.
Thank you, sir, for taking
Thanks a
such.
lot. Thanks for you all.
Yeah.
Yeah. Thank you. Okay. Have a good day. Bye.
Thank you, sir. Have a nice day.